it gets a little old, and once it stops being sort of an ego thing, it starts being rote and boring. So I found that because a lot of what we were doing was repetitive, that there must be some means by which the mechanism of reverse engineering could be automated meaningfully. So I set out on a quest about a decade ago to write an automated reverse engineering and binary modeling system that required no human intervention. Most reverse engineering tools are intended to be driven by a consultant with skill in the art, if you will, and that knows what they're looking at, and is simply looking for a better view to understand the application. The IDA pros and X-rays of the world have the intent of producing a model that is human readable. To generate a model that is machine readable and human readable has proven to be an interesting challenge and the crux of what we've been doing at Veracode. The goal is to make a program searchable for conditions. That way you can use math and graph theory and things like that to weed out and search for the conditions that result in insecure behavior. So with that, I'm going to dig into this topic today and try to move along reasonably quickly. I'm going to be discussing some of the things that we've learned building a binary analysis system that in the event you decide to go trudging down the path of building a binary modeler yourself, you might not make some of the same mistakes we did early on. And with that, it is now 3 minutes of the hour, so I'm just going to get started. So, first, a declaration of vast oversimplifications. Right now, all of the examples that I'm going to be putting up here are going to be taken from an Intel 32-bit perspective. This is merely for clarity. Everything that we do is cross-platform and resourceable and retargetable, as they say. So nothing here is specific to Intel. We also take a C and C++ bias. It was the first platform that I decided needed to be modeled, mostly because at the time it was perceived to be the most difficult to model and to model correctly. I expected to be able to reverse engineer and model Java and .NET and things like that. I did not know when I started whether or not I would be able to completely model C and C++ and all of its language elements. Particularly daunting seemed things like exception handling and virtual functions, virtual bases, and all of the different layout things that were undocumented and getting all of the details right. So there's a C++ bias in the slides. That's my bias. The research to develop the system that is described has taken over 5 years to develop and another 5 more to implement correctly. I can tell you that there's nothing more heartbreaking than 3 years pounding on something that does this kind of thing, implementing what you believed was the most accurate and faithful representation of the current academic best practices for this kind of thing, and realizing that you had missed out on a few really important design elements and have to start all over. So we're going to try to save you that heartburn as well. And so at the bottom there, I've also mentioned that we built the system to be retargetable, resourceable, and pluggable. We don't go into the architecture specifically here, but we're going to be focusing on the design and the algorithms so that you guys can get an idea of what goes into this kind of process. Boring stuff first, yes, we have a patent. The patent covers some of the intermediate representation stuff that we do and some of the early disassembly process that we do. If you wanted to implement your own stuff, I would recommend at least taking a look at that, but at the same point, I'm not saying it's the only way to do what we do. There are probably a few ways to do it. If you choose to innovate in this space, I would choose to innovate in this space as opposed to re-innovating the things we've innovated, for what that's worth. All right, so there are many publicly available things that I'm going to be pointing to that are of interest that I started with. I'll explain some of that at the end, but I owe a great debt to Christien and her doctoral thesis that she published in Queensland University of Technology in 1994. And she initially described a mechanism by which 16-bit DOS programs in C could be decompiled to something reasonable, and described a four-phase process: a front end, a data flow transformer, a control flow transformer, and a back end, which, by the way, kind of looks like the Dragon book read backwards, which is fine, it's supposed to be. Turns out that decompilation and modeling is very similar to compilation in terms of the things you need to be thinking about, but you're taking a very different tack on the way you're kind of thinking about it, the way the actual considerations when you're writing a modeler are very different than when you're writing something that compiles and interprets code. Most notably, you can think of the compilation process as being obviously optimized to produce machine code output, and the decompilation process is intended for human consumption. The kinds of optimizations and assumptions that you end up making are going to be analogous but different. So the components of a static binary analysis system are going to be a binary modeler that produces a model in an intermediate representation, and then some kind of querying or searching system for that model. You'll find that the modeling process is something you can do without sort of ambiguity. It's the kind of thing that you should be able to produce consistent transforms and produce output that does not change the meaning of the program when you do those transforms. How exactly that happens is going to be discussed here. The searching system I'm not going to be discussing today. I have not slides nor time to discuss the mechanism by which you search for flaws. That is, again, another interesting discussion, but worthy of maybe another 2-hour session at some point. So let's just simply talk about how binaries turn into models of binaries. The IR is the most important part here. At Veracode, we use the kind of IR that is a superset of everything that you can potentially decompile. So all of the different language elements from all of the different languages, all of the, everything from a register and it's the way you transfer things from registers, all the low-level stuff, as well as all the high-level things like classes and type information and namespaces and exception handling and statements and expressions and algebra and the meaning of the program. All of that is in the intermediate representation. There are other IRs that are out there that you can use as a point of reference. The research IRs out there are pretty good. Spark, Score, Pegasus, etc. There are reverse engineering oriented IRs, such as REIL, which you probably have heard about. It's gained some notoriety as of late. And you'll see ASTs, RTLs, SSAs, and things like that in things like LLVM or GCC if you were to go delving into the compiler source code. Those things are common in compilers that use multiple IRs. In other words, you build first an AST, and then you transform that into an SSA, and then you transform that into an RTL, and then you produce a binary through a code generator, that kind of thing. Veracode's system does not use multiple IRs. It uses a single IR. And the reason why is one of the lessons here. But just note that there's a single IR that we use to consistently transform. So if you are to build something like this, you may not want to pick up somebody's IR off the shelf. It may have not been designed to represent things like low-level and high-level code at the same time. You may not have a single IR, you may have multiple IRs you'll need to use. And it may not be possible to represent absolutely everything that you need to represent for your transforms in somebody else's IR. If you do that, you might want to be getting something that's open source that you can hack on and add pieces to. I mean, we're always adding little bits of things that we find that need to be represented and that we don't want to lose to the transformation process to our own IR. So this is a living, growing thing. I wouldn't just pick up some static IR out there and start using it. So lesson number one, most IRs are not built for transformation. when they're not optimized for memory use. Expect this to be custom work. The IR can become huge. We routinely analyze programs that are 2 gigabytes in size or larger, but just for the binaries alone. Enterprise code is extremely unforgiving. You'll get stuff that has been built from all over the world. People have binary components that they don't have source code to anymore, that were built many years ago. And you'll find that these giant development teams are capable of producing a massive, massive volume of stuff. And in order to truly model and understand that thing, you're going to need to be able to represent it all in the memory of some kind of system. We use pretty big computers. We have some boxes that have up to 25 gigs of memory in them, in our racks. That said, we debug on machines with 16 to 8 gigs of memory. So, depending on how large the thing is that you really want to model, you have to be capable of sort of representing or eating the whole chicken at once. Piecemeal analysis is not going to do a whole lot of good. There are techniques that we use to eat binaries that are much bigger than that, if absolutely necessary, but in order to transform everything, you're going to have some kind of representation of the whole thing in memory in some way. Linkers and things get away with being able to stitch together a program and produce a binary in a very kind of dumb and lightweight way. They're becoming much smarter. Linkers are now doing things like Postlink Optimizations in Visual Studio 2010 and all of that stuff, where you produce an intermediate representation for the linker, and the linker re-optimizes in whole program optimization form after and writes it all out. That kind of thing is kind of what you're doing when you're building a model. You're going to be, not just unlinking an application, you're going to be modeling the whole thing, so expect that. Desirable characteristics of an IR: attention to size and speed. Don't over-optimize too soon, but rather make sure that the IR has everything you need in it. So for a variable, not just its name and its type, but maybe all of, whether it's been used as a parameter or not, whether it's in or out, those kinds of things. Every little detail about, the context and the information about a variable is going to be important. Debuggability and readability. This is effectively a giant database. If you don't have some diagnostic mechanisms built into it, you're going to be sadly disappointed when things don't decompile well and you have no real good way of dumping chunks or pieces or subtrees of your model in order to figure out what went wrong or why you're suddenly adding a 32-bit integer to an 8-bit one. Those things happen, and to be able to visibly debug is really important. In fact, the first thing and the only thing you may be able to use to determine whether the output is correct is whether it looks good to you or not. It's not like there's some unit test that will determine whether you decompiled correctly. It's going to be like, well, I got the original source code, I compiled it, and now I kind of look at the output. It doesn't mean the same thing. You're going to have to kind of look at that and go, looks pretty good. Complete language support. Every language element is going to need to be in there. You skip something that is required for the representation of stack cookies or something, or namespaces, or templates, or partial specialization for templates, or any little piece. You're going to need to represent every little random language element that you've ever heard of. Every single one. Otherwise, any program of size will encounter the thing you missed and have incorrect decompilation. So don't expect your test programs to be representative of the kinds of things that you're going to get from the outside world. They will have every language element in them, whether you like it or not. You will have to implement exception handling, even though it's terrible. Just get used to it. Single uniform IR. Basically representing everything one way. Every single thing, like a 32-bit integer 0 immediate expression. There should only be one way of representing that thing. That way, you can actually compare two IR subtrees and say that they are in fact the same thing. Being able to reference things like type information using a unique identifier for every kind of type is really interesting. We don't use things like type specifiers where you might say, well, you have an int, and then you make a const version of that, and then a pointer of that, and then another pointer of that. Now, what is that? How do you represent that? In the Veracode internal IR, it's a single identifier. The same way you'd represent an int with like the number 10 maybe internally, we would represent the pointer to a constant the same way with like maybe number 130. We do that with templates. It's historic how we managed to do that, but I'll try to get into it. So why a single uniform IR? The mechanism by which you decompile and model a program is iterative. You will not know everything about the program the first time you look at it. The decompilation itself is necessary to determine what parts of the thing that has been sent to you are code and which parts are data. You will start over from the beginning when you determine that there's more code to be analyzed than you found on your initial pass through. In order to do that, without throwing away all of your work, you need to be able to represent the high-level things that got you the intelligence to make the right choice about code versus data, and all of the new things you're about to import from the binary and model. So you end up with a loop. Basically, this is a code discovery loop by which you perform one arm of a process, modeling everything, and then at the end, you've determined you didn't find it all. There was more things it could be doing, and there's more code flow, there's more control flow and data flow in the program, and that you missed something. There's more instructions. Maybe you were able to determine that a jump to a register was actually a switch statement, and it's got 10 targets. Now, you have to go decompile the body of the switch statement in some way because you didn't previously. So with a single uniform IR, you don't have to throw away your work every time you go through that loop and start over from the beginning just because the IR can't represent what you do. I cried into a pillow for about 2 days after I discovered that and had to rewrite basically the entire IR from scratch. But it was a learning moment, and that's why it's lesson number 2. A hierarchical scoped model is a good idea. The tree should look the IR should basically look like a tree with internal linkage. For the most part, this should be kind of obvious to anybody that's done modern object-oriented programming, but effectively a sort of scoped object view of what you do. So like you have a namespace at the top, that would be sort of the global namespace. Inside of that, you might have namespaces for images. Inside of that, you may have classes. Inside of those things, you may have member variables or procedures. Inside of those, you may have sequences of statements. Inside of those, you may have expressions that can be manipulated, and expressions can contain other expressions, et cetera, all the way down the tree. Of course, being able to reference from one variable to a type is really important, but it's not a parent-child relationship. It's simply a dotted line on a tree. It's a reference internally. So, when you think about why you need references, variables to types, procedures to prototypes, but the hierarchical relationship between types and objects, those are separate kinds of things. They can both exist inside of, say, a class or a namespace. So having that kind of hierarchical representation really helps you, keep things the way that the language was designed. Low-level language elements. You need to be able to represent things like registers and flags, sequences, statements, expressions, things like immediates, references to objects, memory dereferences, mathematics, so just being able to add two things together and store that in some other thing. So transfers of data, set is really important, being able to say A equals B plus C in some hierarchical fashion. And then having that, say, be a statement inside a series of statements. Being able to do things like implement call and return semantics. At some point in the process, you're going to discover that there's a stack, and that there's a stack frame, and that there's, as a result, things that we can call procedures, and that they have variables and returns, and a calling convention, and all of that stuff. Low-level types and data formats, you're going to want to be able to represent spans of bits opaquely without making a judgment as to their type, as well as integers without being able to make judgment as to signed or unsignedness. You don't necessarily know, you just maybe know that two things were added together using an integer function. Therefore, they are probably integer in some way. So, floating points, all of that stuff, doubles, whatever, they're all variants of IEEE format. So you need floating points. You're going to need, complex number representations, potentially, depending on what you're decompiling. And the operations on those, so spans, you're going to be able to need to do sort of the most fundamental things with those, like shifting bits in them. That's actually more of an integer operation. Depending, it could be an implication of sign or unsignedness. If you're shifting to the left, it does not imply signedness, but if you're shifting to the right, there is a unsigned or signed version of shift. You're going to find that multiplying doesn't work the way you think it works. Divide also doesn't work the way you think it works. You'll find that when you, if you're familiar with this assembly, you think of it assigned or unsigned multiply, right? You take two registers, 32 bits, and you produce 64-bit output, and you could have done it with assigned or an unsigned multiply. Turns out that you get the same output, bitwise. The only thing that's different between assigned multiply and unsigned multiply is how the flags get set and interpreted. So zero flag, overflow flag, carry flag, all that stuff. All that matters too. Anytime you decode anything, you're going to be wanting to decode every single minor thing that maybe you didn't think about, like what the carry flag is set to and why it's set that way. That said, when you look at how you define your int, you may not want to think of it as signed or unsigned, because the actual multiply operation performed on that int itself is not really signed or unsigned. It's just going to produce the same output. That said, a divide, much like a shift right, it does imply some particular handling of sign. So in that scenario, divide and sign divide or unsigned divide are operations on those kinds of ints. Idiomatic operations, things like block copying and indexing, basically taking a span of bits out of another span of bits, start and end, just pulling out a chunk. So we're going to use that a lot to do things like A.B, where A is a structure, say, that has 4 integers as members, and you want to take the second one out of it. So you're going to be selecting chunks of spans. So coming up with a language and a description, a mechanism by which you can talk about the operations on bits and on integers and those kinds of things are going to be very important. So high-level language elements are familiar to anybody who's written any kind of code. So types and classes, prototypes are the sort of type of a procedure. Classes are the type of a class. In things that are more dynamic, like Ruby, if you're going to model that, you're going to find that you have classes which are really meta classes, which are a mechanism by which an object can be, where the classes in the system themselves could be first-class objects. So this is cutting out a little bit. Thanks. Okay. So objects have are things like variables and procedures, and you can say that an object has a type. So variables have a class, and procedures have a prototype. Namespaces could either be named or they can be anonymous. Named namespaces are going to be like std for the standard C++ namespace and things like that. So, but also in Java, for example, you'd be seeing things like the Java namespace inside of that. You name it, all of the different hierarchy there. And templates are going to be required in order to represent the kinds of C++ metaprogramming stuff that you're going to see out there. So you're going to need all of that in your IR. We're going to move a little quickly now. Expressions and statements are sequentially executed pieces of code. You're going to find that expression evaluation and calls and returns, traps like interrupts and returns from those things, throws through exception handling, loops, switches, if statements, while loops, all that stuff, they're all statements in some way. Basically, statements are sequentially executed in sequences. You can think of it that way, because basically the CPU says that there's an instruction pointer and that it's marching forward. That's basically all it does, until it's told to do something else via a control statement in some way. So to simulate that, we just basically use a sequence. Expressions are hierarchical and represent arithmetic. You need to be able to represent things like a plus a function call to the function foo, passing it 3. That kind of thing is an expression. So you see in there immediates like 3, operations like plus, also operations like calling foo, and as well as object references to things that are variables like a and b. So building that expression hierarchy needs to be in the IR. Namespaces and sequences. Basically, namespaces are used to collect objects in an unordered fashion. The property of a namespace is that it's got a set of things in it, not a list. It's just a set. You can say, yes, I'm in that namespace, or no, I am not. Sequence is something that is in an ordered fashion. Specifically, you're going to end up using this a lot for sequences of statements, but it could be used in any other context that requires an ordered set. Sequences are useful for building basic block graphs. If you don't know what that is, it is a mechanism by which individual statements are coalesced into blocks that all must execute if a single one executes. So if you have a series of 10 statements with no other control flow, or they have no inbound control flow that could potentially result in a different execution of those things, they are coalesced into a single block. I'm not going to get into that too much, but it's a mechanism by which a large amount of modeled output, in terms of its control flow, can be represented and make it a little simpler and easier to visualize. It also improves the speed of algorithms when you can operate on whole blocks at a time instead of individual statements. So namespaces, again, are used many times when segmenting code by image, object file, source file, or whenever divisions are convenient. Objects and types, I've already kind of gone over this a little bit. Classes are the type of a variable, prototypes are the type of a procedure. Registers I consider generally typeless. They could contain anything. You could take a float and put it into EAX if you want it. It's not like the register imparts some sense of type. It's the operations that operate on those registers that impart some sense of type. So if you were to simply say that EAX is int in some way, or a span of bits but not a float, then the first time you see a float go into EAX, you're going to be very confused. Don't unnecessarily impart type information unless you absolutely have to. So variables are a high-level construct because they can be free of a low-level representation. This is an important note. The idea that variables, as a high-level notion, could have multiple low-level representations is key. You can't simply say, this variable is in EAX. It may be in EAX for its entire lifetime, but it may also be in EBX and then put on the stack and popped off and then put back in EAX by the end of the procedure. That means a variable could have what we call multiple matching expressions. The match expression is what you could write out to represent the variable if you weren't using it. So EAX, for example, could be used to represent int x, but only at a certain spot in the program. So a really important matching expression is the one at the top of the program, at the top of the procedure. If you're looking at arguments and return values, there's only one place, say, the first argument could be located. One expression, one match expression that could represent that first parameter. And let's say that in many cases is like, if it's on the stack, it'd be like ESP plus 4 or whatever. There's some spot where those parameters are going to be at. And it doesn't matter how you got there, they always have to be in the same spot. So noting when you can use a match expression to represent a variable is important, but note that over a variable's lifetime, it could have multiple potential match expressions. The match expression at the start of the variable's lifetime is a very important one, and potentially the match expression at the end of its lifetime for the purposes of doing things like calculating whether or not it returns from a procedure or not. Procedures are a function, lambda, block, etc., and are they're basically the base unit of interprocedural control flow. Effectively, when you write a function, the unique property of a function is that it can call other functions, passing it parameters and accepting returns. Discovering the mechanism by which you discover how many parameters you have and how many return values you have is of interest. and also where those parameters are located. One cannot simply expect things like standard calling convention or CDECL or fast call conventions. These calling conventions you see discussed are only valid for external procedures. Anything that could be considered a static procedure or is internal in some way and the compiler knows it could have its calling convention optimized and switched around, and you could be passing parameters and registers instead of on the stack. So you can't make any assumptions about how a procedure is called until you understand everything about how it's been laid out by the compiler. Templates are the blocks of IR scopes that make generics and or instantiable things. If you use templates to represent things like integer types, you could have integer as a template and instantiate it on the number of bits, for example. This gives you int32 as a single ID, much like, and int16 as a separate unique ID, and int8 or int whatever. But it means that you don't have to define int a million different ways just because it has different bit widths. So using the language elements to your advantage in the way you define your basic typeset that everything derives from in your hierarchy saves you a lot of time. This allows you to use very specific precision without complex type selectors. In other words, if I say A equals 3 and 3 as a particular type, I don't have to use like a really crazy series of things to represent that type. I can just use a single identifier. So the good IR enables data flow analysis, control flow analysis, expression and statement manipulation, serialization in parts and as a whole. You should be able to take chunks of this model and save it out to disk and pull it back in and have it be the same thing. Also, good debugging. So if you are going to make your system multi-threaded, you should start with a thread-safe IR. This is going to be the big thing that prevents you from being able to do multi-threaded transformation or being able to lock subtrees of your model. If you choose to go for speed, or you decide to run as a single process, you can avoid this. But if you're going to be multi-threaded, got to start here. You're not going to want to implement it after the fact. You'll find that it is both painful and unlikely to ever get done. So that was lesson 4. Data flow representation. Data flow, control flow, and structure are the things you are going to find to define your model. Structure is your IR. The data flow representation is a connection of definitions to their uses. So if I say x equals 3, and then I say a equals x, those two x's are connected to each other because one defines x and one uses x. That's the basis of data flow. You're going to find that definitions connecting to uses, and then the uses on the right-hand side of a set to the definitions on the left-hand side of a set or an assignment are going to be able to produce def use and def kill kinds of things. A def kill is when another definition comes in, like x equals 3, x equals 4. Well, it's not like you're using the x the second time that was defined the first time. You're simply blowing away its definition. That would be a kill. So you have defs, uses, and kills. You represent everything that way, and you end up with the kinds of graphs you can use to determine whether or not the program's meaning is changing when you're performing a transformation. If the def use connections that you see there, if you operate on that graph rather than the model directly, you won't change the meaning of the program unless you intend to. So do yourself a favor. When you make a DU graph that don't make yourself a DU graph that incrementally updates itself. It's tempting that when you make model changes to have the things like the DU graphs automatically update themselves. Don't bother doing that. What's better to do is to batch all of your IR edits and make the DU graphs read-only. You're going to be using the DU graphs a lot. What you want to do is they're computationally intensive to build. You're going to be propagating definitions downward on your program and uses upward like that until they meet each other and form connections. That can be very complicated for large procedures. Try doing that with a hash function like MD5. Think about the amount of data flow there. By definition, it's extremely complicated. The first time I implemented that, it took 4 hours to build the data flow graph because I did it all terribly. But the second time around, I only built one data flow graph and was able to make any changes I needed, simplifying the graph, and then rebuild the data flow graph as minimally as possible. So really try to make the DU graphs read-only and batch your edits. Let's see, control flow representation. Control flow should be flexible. You're going to be editing this a lot, so make distinct interprocedural control flow. You're going to find that low-level control flow should be simple, and that high-level control flow is not going to be simple at all. To simplify how we've done this, we built a program counter, or a cursor object that represents where the instruction pointer would be and what it can possibly do. It's a class that you can point into the model and say, start here and tell me where you can go. What's the next things you can do, and what are the previous things you could have come from? And that way you can kind of cursor your way around the hierarchy. This means executing things in evaluation order. So that means when you say A equals B plus C, you evaluate B, you evaluate C, then you evaluate the plus, then you evaluate the equals. So that kind of thing. Having this kind of cursor object makes intra-procedural control flow a lot easier. Pairing that up with a stack frame object that represents a call stack, that together can vastly simplify how you look at inter-procedural control flow. Expression and statement manipulation. If you design your statements to be effectively linear flow, non-hierarchical entities, and use less sequences to provide hierarchy, statements are easier to manage. Lesson number 7, if you ensure that no expressions can be referenced outside of a parent-child relationship, you can manipulate them much easier without worrying about managing back references. When you see something like A equals B plus C minus C, you may want to do the algebraic simplification of removing the plus C minus C. If that the C in one of those two C's could be referenced by some other object other than its parents, you'd have to worry about what it thought about that elimination. You wouldn't be able to perform it. You wouldn't be able to have, if somebody was referencing something that C knew about, you wouldn't be able to eliminate those two expressions. You would be affecting something off elsewhere else. You're better off keeping expressions from having references that come into them only by their parents. If you do that, then you can say simplify an expression, and all you have to worry about is the things underneath the parent node of that expression. You don't have to worry about what the rest of the world thinks about your expression that you have there. Serialization, again, make sure you can back this all up. Nothing is more depressing than running for a day on a big client application or something and then not having a checkpoint that you can say, oops, we got to go debug this thing or whatever, and you don't have a place that you have to run it again for a day every time you make a change or something like that. That's not tractable. So make sure you can save as you go. So constraints of the real world, vector math, kind of crazy. You're going to end up implementing the entire Intel instruction set and the entire ARM32 and thumb and everything else. All of the vector stuff that they don't talk to you about. Extreme use of templates. Everything that you could possibly do with a template, someone's going to do it. So you're going to have to be able to represent every little detail of how instantiation happens. Optimization. All your binaries are going to have some code that's optimized and some that's going to be not optimized. You don't get to pick. So expect that you're going to have to be able to handle optimization. That means rewriting function signatures. That means interleaving of instructions so that, to implement better pipelining, that kind of thing. It's all going to happen. Things like frame pointer elimination. I'll give you the hint. Don't ever rely on the existence of a frame pointer. All of this is possible without using the frame pointer. You create a virtual frame pointer mentally by looking at what the stack pointer's location is at the beginning of the function and use that as your basis to represent the entire stack frame. Don't ever use a frame pointer. You'll note that the frame pointer falls out automatically because if you simply base things off the stack pointer at the beginning of the function, that one of the first things you'll see in a very standard calling convention is moving the stack pointer into a base pointer. Happens. That way, effectively you're seeing the compiler do that. But if it didn't do that, you need to be doing it manually. So keeping track of where the stack pointer is in a function is going to be really important. You must implement every language element because you will encounter all of the things. So, binary modeling. Compilers make assumptions. This is very important. The compilers themselves are going to make certain assumptions. The modeler takes in the output of a compiler, not arbitrary input. So you can use the assumptions the compiler makes to your advantage. You are not decompiling arbitrary binaries. You're decompiling things that come out of a compiler. You may end up running into the case of, well, what about malware? What about things that people have done by hand? I'm restricting the definition of a decompiler to something that takes in the output of a compiler. There are things that you could probably generate that execute, but are provably not coming out of a compiler. We can get to that. On x86, you can assume the call mechanism uses the stack, and that the stack goes backward, and that external functions follow a set of known calling conventions, and that non-external functions can have arbitrary calling conventions. Those are things that the compiler has basically made as rules. That's the way it's going to generate it, that's the way it's going to work. You have to be able to make the same assumptions the compiler made. You should also not make assumptions the compiler did not make. Don't oversimplify the problem. It will be more complicated than, you'll find that when your assumption is wrong, that all hell breaks loose. So the input to the modeler: executables, linked libraries, environments, and debug symbols. Environments are going to be the things that you do not decompile. You'll find that when you compile, you don't really think about kernel 32 a whole lot. There's some functions in there, but you have to draw a line in the sand between what you care about in terms of your modeling and the things you don't care about. That's on the stuff on the other end, those are your environments, if you will. On that edge of between things, we need type information. You need to know how you get from your code to printf in libc. You need to know that if there's a const char star or whatever in there, and that it returns a whatever, and that it goes there via cdecl calling convention. Those things were known to the compiler at the time of compilation. They would need to be known to you at the time of decompilation. So when you build environments, you need to imbue them with type information. Guess what? That means you're probably going to end up writing a C++ compiler as part of writing all of your environments. You might not write the whole thing yourself, but you may end up instrumenting LLVM or GCC or something like that in order to get the type information out from the header files. That way you know what create file does. You're going to parse windows.h in all of its little pieces. So environments have a pairing of two things: an external dependency in some way, and type information for the edges of those dependencies. Many times, you can get external dependencies declared in the form of mangled names, for example. Those will have type information in them. Writing a demangler that unmangles mangled names is of use. Being able to match up mangled names that are exports with the things that you have parsed in the header files are going to be key. So you can make, you can parse all of windows.h and stdio.h, and you can get printf and all of its, modeled IR glory, but then you have to actually match it up to the real binaries model, like the real actual binary bits, and where its entry point is and things. So being able to demangle mangled names is really important. Environment compilation, you're going to end up building a list of DLLs. Again, header files, we kind of went over this already, but C and C++, you're going to end up pairing up all the DLL exports with things that are in header files. The modeling pipeline is a front-end environment loader with a data flow transformer, a data flow optimizer, a control flow transformer, and then an optional back-end source generator. Again, if you're not going to have human beings looking at the output, you don't need to do the last step. If you're going to be using completely modeled, automatic scanning system like Veracode has, we don't have to generate that part. We just make the model, leave it in the middle, and then start scanning it right away. Platform-specific front-end loader will pull in any kind of type information and debug symbols and RTTI information that you might have. There's a tremendous amount of valuable type information in things like RTTI information and other languages, things like Objective-C tables. So the demangler here has all that type information in it. Undname in Microsoft Visual Studio land will give you an interpretation of that. Reverse engineering that is left up to the reader here. So data flow transformation. There's an import process, variabilization, propagation and merging, code discovery, call conversion, and reference conversion. Import is the mechanism by which you decode an executable on all of its assembly instructions to the IR. You're going to pull apart add to the operation add and all of its individual flags and things. Variabilization is the mechanism by which you take a low-level representation of the data flow, so dereferences of things, the registers, dereferences of registers, dereferences of memory, and turning those into high-level variables. Propagation and merging is the mechanism by which the data flow becomes more high-level and actually connected. So all of the definitions and all of the uses get paired up, and you'll find that EAX used, definition defined in one place and used in another place are actually the same EAX because their lifetimes overlap. A use has a lifetime that goes upward, and a definition has a lifetime that goes downward. When those lifetimes intersect, they become the same variable. There's a form called single static assignment form that you're going to find in optimizer texts and things inside of program representations that inserts a phi function at the point where two conflicting definitions come into a use. I prefer not to do that. I prefer to eliminate the phi function and simply merge the variables together. They are in fact always the same variable. A single use of two different definitions does specifically mean that they were all the same variable together. Doesn't matter how you get there. In fact, Java makes that a verifiability requirement. C and C++ always do it from a compiler standpoint. You could probably generate some assembly in which that's not true. However, you'll find that in practice it never happens. Code discovery is the mechanism by which you find where a jump to a register or a dereference goes. Call conversion is the mechanism by which a procedure where you have discovered arguments and return values that there is actually a function, and that there are calls. The calls to those things take in particular parameters. Reference conversion is the mechanism by which, once you've discovered all of the variables in the system, that there is places where you've taken the address of that thing, like ESP-12. If there's no dereference around that, you wouldn't know that it was a variable. It's not. It's the address of a variable. So finding all of those, globals, etc. I'm going to skip through some of this because import is pretty straightforward. You're going to find that you are importing everything that you think the instruction pointer can reach. Just do a greedy algorithm. You walk the instruction pointer forward. When you find that you can't tell where a call goes, you stop. You don't know that it returns. Many calling conventions don't return. The compiler knows that at the time of compilation and will not generate some magic happy place for your instruction pointer to land after that call. It'll just stick another procedure there. So don't do that. Until you know where a call goes or how it goes there, don't expect it to always return. Variabilization is the process by which real variables are created to represent low register and memory access. I'm going to have to skip some of this. We can discuss it over a beer anytime. But we start with a whole variable for each def use site. A EAX is its own variable when it's defined, and then the use of that variable later is its own variable until you prove that they are in fact overlapping lifetimes, and then you can merge those variables together. The goal of a variabilizer is to create as many variables as possible, and then merge them until there's only as many variables as necessary. Don't be afraid to create too many variables at the beginning. You can end up merging them together. It's the only operation you're going to perform. You're going to merge variables together as you discover the fact that they are in fact the same variable. So you're going to find that there's a trick here to measure all allocated variables that are on the stack with reference to the base of the stack frame. I mentioned that. Use ESP at the top of the procedure. Don't use EBP, ever. So range propagation is what you're going to use to determine where things are offset. If you see an EAX that has been set to by some crazy means through the procedure, ESP plus 8, you'll find that as a second argument, but only after you've done the math to determine that that dereference of EAX or whatever that ESP was, plus 8 was set to, was in fact set that way. So propagation and merging is the mechanism by which we push the frontier of definitions downward and the frontier of uses upward. As they merge and the frontiers collide, you can do merging of those variables to show that they are in fact the same variable. I already talked about this lesson. So variabilization is like SSA form, except instead of generating 5 functions, we merge. That's the operation. Interprocedural propagation is the same kind of thing, except you're going to find that things that are used basically before they are defined are parameters to the function, and things that are defined and then are used outside of the function are things that are returned. So as you propagate intra-procedurally first, and then propagate inter-procedurally. That'll help you find any connections you make between the function and its caller, and find that the data flows create arguments and return values. Code discovery. Lesson number 11. The compiler didn't know where virtual functions were going when it built the binary, and you don't have to know where the calls are going either. You have to just know where the how they got there, the mechanism, the calling convention. You could have 2 binaries, A and B, one built 20 years apart from the other. And the compiler could still make binary A, and it would do something. It just wouldn't know where that virtual function call went. If the thing was, the object that you're making the call on was declared in B, and it was written like 20 years later, you could totally make it go anywhere in the world. So don't worry about not finding where every call goes. And until you put all the pieces together in the decompilation at the very end, do you care, really? The compiler didn't care about where the calls go. They don't care where the jumps go. They just know how they go there. The analysis process does require a more, searching for security vulnerabilities does require knowledge of where those calls could potentially go. That's a completely different thing. It's not relevant to the modeling process specifically, so don't concern yourself with it. I'm going to skip call conversion for now, but the idea is that calls turn into operations. The low-level notion of a call statement turns into the high-level notion of a function evaluation. And then that calls that go to many places have an expression that say where they go, and you're going to have to do some range propagation to figure out where those things end up if you really care. Reference conversion, going to skip this for the most part. It's the mechanism by which low-level EAX plus 824 turns into the address of A bracket 100 dot B bracket 2 dot C. So it's applying the type information to a layout with an offset and finding an expression at the high level that can be reproduced to represent a low level variables match expression. Type voting is all propagation. Effectively, the goal of type voting is to ensure that all variables have the most optimal type. You're trying to minimize the number of type casts in the program. If you were to simply make all of your variables spans, there would be typecasts all over the place. If you make them, something an int, and you assign a signed int into it, now you're fighting, because you don't know if the container is signed or if it's unsigned or what. But there's going to be a cast because the thing on the right of the assignment has a different type than the thing on the left-hand side. So minimizing typecasting, and I don't mean like the things that do type extension. So if I go from a signed int to a 32-bit int, from a 16-bit int to a 32-bit int, you're going to find that the compiler represents that as a cast, but also a sign extension. Don't confuse casting with the operation of that a casting in a language like C performs on stuff. So running out of time slowly, but I'm going to quickly breeze through optimization. The idea here is that you're performing expression simplification. You've created a model with every variable in gory detail, but what you haven't done is start simplifying the representation. So if you see things like, again, A equals B plus C minus C, you're going to end up eliminating that. If you have dead code or you have expression forwarding happening, effectively, if you say A equals B and then C equals A, you could turn that into C equals B, as long as A is not used. I'm going to make a recommendation that if anyone wants to get into these optimizations and how they work, that you read Christien Cifuentes' thesis. I'm going to forward through some of these here so I can get you the link. And I'll put these slides up for you. Right here, her decompilation thesis is fatcode.net/res/228/file/decompilation thesis, decompilation_thesis.pdf. That is worth your time if you have any interest in this material. There's a lot of material here that I couldn't possibly get to in an hour. It takes a long time to get this to work. I've spent a decade of my life making it work. Today, if you got started, you could probably get something functional in 4 or 5 years. It's worth doing, but I can tell you that it's not for the faint-hearted at all. That said, for those intellectually curious, feel free to read that thesis, and there's a little spark in there when you start realizing that this is all possible, and at some point